of the important parts of the electrical system is the dashboard. So what basically the dashboard is it's the user interface for the driver to control the car. So if you have a look at this thing over here, this is the dashboard. And the reason why it's loose like this is that when the top shell comes on to the bottom shell, there's a space for it to fit on like that. So it fits right here when the top shell is on. So you'll notice that there are a lot of different buttons, and one might be a little confused at first as to what one button or the other does. So to be a driver, the driver has to go through a training where we'll tell him exactly which buttons to press in what order. So just a general overview. We have some buttons over here which initiate the car. So it turns on, it connects the auxiliary battery pack to the system, and we have a start button here. So this is basically like an ignition of the car. So once we set all these other switches up in the correct order, when we finally want to start the car, we press this green button over here, like that. We have some other lights here, and these 4 lights represent warning signals from the battery protection circuit. So if, for example, we're over voltage or under voltage, one of these lights will light up and let the driver know something's wrong. We also have these neat little displays which display the speed of the car and the current drawn from the motor. So essentially how much power the car is using at any given time. And over here we have some other buttons. For example, this is the horn button. We have speed control buttons over here. And in the middle here, it's not attached at the moment, but this is where the rear view camera goes. So that acts as a rear view mirror, but only we use a camera.
Probably the most important part of the solar car is the solar array. What we use are 468 SunPower A300 cells. And we have 3 separate strings that are all in series, and they feed the 3 different PowerPoint trackers. And basically, there are a few different types of modules on the car. We solder together all the cells into those module settings, ship off the cells and have them encapsulated with EVA, TEFCell, and TEDLAR. And then we take those completed encapsulated modules and put them on the car. And every 3 or 4 cells we have bypass diodes to allow current to continue to flow even if one of the cells is covered, not receiving sunlight, or if it's broken. So the system's pretty robust. If one part of the array isn't working, at the worst, at least the other 2/3 are.
Aside from the array, another really important part of the solar car is the motor. That's what allows the car to drive. So what we have here is a 96-volt brushless DC pancake motor. So they call it a pancake motor because it's really flat, and it's really flat like a pancake. So you can see this thing right here. This is the motor. It's really small and compact. Now something special about this motor is that it allows us to drive the wheel without a transmission. So what that means is, instead of having a set of gears or like a bicycle chain driving the motor, connecting the motor to the wheel, it's just the motor onto the wheel. That way there's less energy loss in the system. Now you might think, how do we change gears then if we don't have a transmission system? Well, turns out what we have is we have our own version of a transmission, which we call the air gap. And so what the air gap is the gap between the electromagnets and the coil, the permanent magnet. And so what happens is, if you vary the distance between those 2 components, you get a different set of speed torque characteristics. And so if you zoom in over here to this little knob, this is the thing that controls the distance of the air gap. So by turning it one way, we're closing the air gap, And the closer we bring the air gap, the smaller the air gap is, the more torque you can get out of the motor, but the less speed. And now if you bring, so that's like you're in low gear. And if you bring the air gap far apart, if you make the air gap very big, it's like going a gear up. So you're going from first gear to second gear to third gear. And we control that with some circuitry in front of the car. So basically the driver will press a button to say he wants to go to first gear, to second gear, to third gear. Now how we control this motor is we do it through a motor controller. So we have this thing that's a black box, and we call that a motor controller. Now we don't have it right now, but essentially it's just a black box that sends commands to the motor in order to move it. And we control the motor controller with our own onboard computer. So we program that computer, and that computer sends commands to the motor controller, and the motor controller sends commands to the motor. And that's how the motor works.
So we've got various electrical boxes along the side of the chassis here. In this first box is where we plug the 3 array strings into, and this leads to our power point trackers here that are basically fancy transformers that determine exactly the amount of power that we're getting out of the array and match that power up to the voltage of the charging voltage of the batteries, so we get the optimal power from the array. And then in this second box over here, we've got a couple of relays, our main relay with the main fuse, and our array relay that basically control, that the BPC controls in order to keep the battery safe. On the front of the car here, we have our telemetry section. First, we have a serial modem that is controlled by our Wolf onboard computer and sends real-time information to a computer in the leader chase vehicle to pick up and monitor battery temperatures, currents, voltages, as well as other information from the car. And we also log that data to a SD card for later use because the information coming from the serial modem tends to be a bit lost.
The battery pack of our car is at 96 volts, and that charges our 96 volt motor. But it turns out we have lots of other circuits in the car. For instance, the motor controller circuitry, the air gap circuitry, turn signal circuitry, that don't use 96 volts. They use much lower voltages, like 12 volts, 5 volts. Now what this box does is it allows us to take the 96 volts of the battery pack and converts that 96 volts into 12 volts and into 5 volts, and in order to power the rest of the circuits. So if you take a closer look at this circuit, this is our main, we call it the DC-DC converter board. So 96 volts comes in from one place, and this is a DC-DC converter. It takes the 96 volts and converts it into 24 volts to power the air gap motor, whereas this chip over here takes the 96 volts and converts it into 12 volts and to charge to power the various other circuits on the car. Now the last step of this circuit is to take the 12 volts and convert it into 5 volts to charge the other circuits that are charged by 5 volts. And right next to this DC-DC converter, you'll see another DC-DC converter board, which pretty much does the same thing, but it's powered not by our main battery pack, but our auxiliary battery pack. So we have a small battery pack on the side of the car, and we're allowed to use that extra battery pack to power our horn, to power our user display interface, and various other circuits. So we use the energy from that battery, goes into here, and we regulate it to 12 volts, as well as bring it down to 5 volts. So essentially what we have here is, once again, we have high voltage coming in, and these boards convert it to low voltage.